Namaskara. In this session, we continue our discussions on the analysis of the recurrence equation. T of n is given by T of floor n by 2 plus T of seal n by 2 plus n minus 1. This is the recurrence equation. What we want to show is that T of n is less than or equal to n times seal log n. So, this proof technique is called guess and verify. Because the recurrence equation is a bit complicated and we are finding it difficult to solve exactly, we are trying to get upper bound. You can get weak upper bound. To get a strong upper bound, you have to do a bit more hard mathematics. We have seen that by solving over an infinite sequence and using monotonicity, we have come up with some proof. That is one way of proving. This another way of proving, guessing and verifying. We get this guess based on our experience and based on the solutions of similar equations and so on. Okay? That is why it is called guess and verify. Our guess may or may not be correct. In that case, you have to adjust your guess and then arrive at a function that is very close and acts as a bound for T of n. This is still not an exact solution. This is an upper bound, but this is a very close upper bound. Okay? T of n is less than or equal to n seal log n. We are going to prove by induction. It is a strong induction. In fact, assume that T of k is less than or equal to k times seal log k for k equals 1 to up to n minus 1. Assume that this is the induction hypothesis. Now we have to show that T of n is less than or equal to n seal log n. This is what we have to show. It is going to be a very clever manipulation with the floor functions, seal functions, pattern and so on. It is a pure mathematical exercise. From this point onwards, okay, it is a good mathematical exercise and working with inductions and so on. The algebra you have to follow carefully and observe carefully the steps that are carried out to understand what actually is going on and how we prove it. It is a clever proof, a bit tedious, but still a clever and neat proof. Now, T of n is less than or equal to, it is exactly equal to n minus 1, I can make it less than or equal to this. So, T of floor n by 2 plus T of seal n by 2 plus n. You can see I have replaced n minus 1 by n, I made it larger. So, the right hand side is larger, left hand side is smaller than or equal to. So, it is an upper bound T of n. Now, by induction hypothesis, I am going to get the bounds for floor n by 2, seal n by 2. Floor n by 2 is smaller than n, seal n by 2 is smaller than n. Because of that, I can apply the induction hypothesis, and when I apply the induction, watch carefully what I have written. What is induction hypothesis for floor n by 2? You have to set k floor n by 2. That means floor n by 2 seal of log floor n by 2 k seal log k. K seal log k is written like this, plus k in this you have to substitute seal n by 2. So, seal n by 2 times seal log seal n by 2 plus n. This n is written as it is. So, how do I get these two steps? I get this one, I get this step by induction hypothesis. I applied induction hypothesis for k floor n by 2, applied induction hypothesis for k seal n by 2, and I have got this. Now, I am going to replace this smaller value with a larger value. This is a larger one, because it is log of floor, I replace it with log of seal. Therefore, this is less than or equal to floor n by 2 seal log of seal n by 2 plus seal n by 2 seal log of seal n by 2 plus n. Now, you see that this term and this term are same, I can pull it out. So, when I pull it out, I get this is equal to seal log seal n by 2, this is pulled out, floor n by 2 plus seal n by 2, you will get from the first two terms, the common value is pulled out, but you know that this is n for all n, this is n, therefore, this is equal to n times seal log seal n by 2 plus n. So, I have nearly, I want to show that it is n log n, seal n log n, but I have shown that it is less than or equal to some expression. We will see how this is related to n. I have n by 2, I have log seal n by 2, but I want to know how it is related to log seal n, because I want something like n log seal n, that is what I want. So, the natural thing is to see the relation between these two, all right. The first observation is n, now I will do a separate calculation here, n is less than or equal to 2 power seal log n. For real numbers, actually n equal to 2 power log n. N equal to 2 power log n, that is a basic fact. Now, this log n may be a real number, I am taking seal. So, I am taking to the larger number. If log n is an integer, it will be the same integer. If log n is 7, it will continue to be 7. If log n is 7.3, seal log n will be 8. Therefore, n equal to 2 power log n, but n is less than or equal to 2 power. Right hand side is also an integer, right, seal is an integer. Therefore, n by 2 is less than or equal to 2 power seal log n minus 1. I am dividing by 2. Because of this, ceil n by 2 may be a fraction, but ceil n by 2 is less than or equal to 2 power ceil log n minus 1. This is because this is an integer, right hand side is an integer. Ceil of an integer is same number, okay. Ceil of 10 is 10, ceil of any integer is same integer. So, when you take ceil, I get the same integer. Now, you take log, because I have log ceil n by 2 here, therefore, log ceil n by 2 is less than or equal to ceil log n minus 1 when you take. Therefore, I have one very interesting observation relating log ceil n by 2 with the ceil log n. Okay. Now, right hand side is an integer. So, again when you take ceil, you get the same bound, ceil log ceil n by 2 is less than or equal to ceil log n minus 1. This is because this is an integer. Ceil of an integer is the same integer. Okay. So, you take ceil on the left hand side, ceil on the right hand side. In the right hand side, because you have an integer, the ceil is the same value. That is the reason why I get the same bound. So, you see that this I can write less than or equal to n ceil log n minus 1 plus n, because this value is less than or equal to ceil log n minus 1, and this is equal to n ceil log n minus n plus n, and they cancel out, and this is equal to n ceil log n. That means it is less than or equal to, this implies T of n is less than or equal to n ceil log n for all n. The proof by induction is complete now. I have assumed T of k is less than or equal to k log n for all values smaller than n, applied the induction hypothesis, and then I got a bound for T of n. That means proof by induction is complete and T of n is less than or equal to n ceil log n for all n. See how, because I guessed the correct function, the proof worked. Suppose I guessed a wrong function, you will be stuck with the proof. In that case, you have to adjust the function and you have to find, it is only guess and verify. If your guess is correct, you will be able to mathematically complete the proof. If your guess is wrong, you will be stuck. You have to abandon that guess and make another guess, and so on. It is a trial and error method. So, when the things are very complicated, you look for alternative ways to get an idea about T of n. So, what we have done so far is the following. We have a complicated recurrence equation for T of n. We used monotonicity and values of Tn for an infinite values for n equal to 2 power k, k equal to 1, 2. So, what you do is you find exact values for n equal to 1, 2, 4, 8, 16 and so on. But what about an in between value? You have an expression for n equal to 2 power k. So, you used monotonicity and the values for an infinite series of values to get a bound something like that, something like T of n is less than or equal to 2 n log n minus n plus 1. This bound is true for all n. Instead of working on an infinite values, looking for monotonicity and all, guess and verify directly, but you must guess the right function. Assuming you have guessed the right function, T of n is less than or equal to n C log n. It is a beautiful upper bound. This also is done for all n. This is also proof by induction. This is guess and verify, okay, guess and verify. So, you can see that how we are getting upper bounds, different techniques we are using get bounds to get an idea about T of n. What is the growth rate of T of n? It is like n log n, right. So, from all these things you are able to guess that T of n is order n log n. This you are able to guess in variety of ways. But now we are going to derive the exact expression for T of n. Sometimes that is needed when you have two algorithms that are having competing, when they have the same order and all the order notation are hiding a constant, and we have to know the constant to know the difference between the efficiencies of the algorithm. For example, algorithm A may be order n square and algorithm B is also order n square, but 10n square is also order n square, 1000n square is also order n square. So, even if it is theta, the same comment, 10n square is also theta n square, 1000n square is also theta n square. So, this could be 10n square and this 1000n square. But 1000n square algorithm is obviously worse than 10n square algorithm. So, it depends on the constant that are hidden. If you are getting big O and theta notation through bounds, you get some asymptotic idea, and if you want to really compare and want to choose the best, you need to do a thorough tight analysis. So, we have to solve T of n exactly, that is what we are going to do. It is more complicated and challenging because it has got floor function and seal function, okay. T of n is T of floor n by 2 plus T of seal n by 2 plus n minus 1 and T of 1 equal to 0. This is what we want to solve exactly. So, if you look at the dependency, right, let us try some simple example to see how the T of n values are related. So, let us consider T of, what is T of 41? T of 41 is T of 20 plus T of 21 plus 40, that is a constant, forget it. T of 40 is T of 20 plus T of 20 plus 39. What about T of 39? T of 39 is, floor is 19, T of 19 plus T of 20 plus 38, okay. So, if you see the following is happening, let us say what is T of 38, this is T of 19 plus T of 19 plus 37. The following observation is very clear. These values are equal. These values are equal. T of 19 here and T of 19 here. These values are equal. In other words, if you write T of n equal to T of floor n by 2 plus T of seal n by 2 plus n minus 1, and T of n minus 1, the next element, is T of floor n minus 1 by 2 plus T of seal n minus 1 by 2 plus n minus 2. These two should be equal. This expression and this expression are equal. In other words, we must have floor n by 2 is equal to seal n minus 1 by 2. Is this happening in general? Here it is happening for 41, 40, right? Whatever is sitting here and whatever is sitting there, they are same. So, whatever is sitting here and whatever is sitting there should be same. That means floor n by 2. And there is another observation. If you see across from right to left, here you have 21 and 20, one less. Here you have 20 and 19, and here you have 20 and 19. In other words, these two, they differ by 1. In other words, seal n by 2 minus 1 must be equal to floor n minus 1 by 2. Is that so? Let us first do that simple proof. We have seen some examples, we have seen a pattern, we will confirm that mathematically. In other words, we are going to show that floor n by 2, floor n by 2 equals seal n minus 1 by 2, and then we are going to show that floor n minus 1 by 2 is equal to seal n by 2 minus 1. These two facts we will show independently. Then we can apply it in our analysis. How to prove this? Very simple. Okay. N is either even or odd. So, if n equal to 2k, left hand side will be 2k by 2 floor, which is equal to k. Right hand side is 2k minus 1 by 2, which is equal to seal of k minus half, and that is equal to k. Seal of k minus half. From k you have subtracted a fraction, but when you take a seal you get k back. Therefore, left hand side equal to right hand side. Similarly, when n equal to 2k plus 1, what is left hand side? Floor of 2k plus 1 by 2, that is equal to floor of k plus half. Floor of k plus half is k. It is like k 0.5. Take floor, you get k. And right hand side is n minus 1 is seal of 2k by 2, which is equal to k. LHS equal to RHS for all cases. Therefore, this is true, you can have an identical proof for this, n equal to 2k, n equal to 2k plus 1. For example, if n equal to 2k plus 1, what is left hand side? 2k plus 1 minus 1 is 2k. So, floor 2k by 2, that is equal to k. This is left hand side. What is right hand side? What is ceil n by 2 minus 1? Ceil n by 2 minus 1 equal to ceil 2k plus 1 by 2 minus 1, that is equal to ceil k plus half minus 1. Ceil k plus half is something like k 0.5. When you take ceil, you get k plus 1 and minus 1, and that is equal to k. So, left hand side is k, right hand side is k, they are equal. You can prove for the other case n equal to 2k very easily. In other words, we have these two facts about the ceil and floor values. We can use this to get something very interesting. Okay? Now, you see what is T of n minus T of n minus 1. What is T of n minus T of n minus 1? T of n minus T of n minus 1, I will physically write T of n is T of floor n by 2 plus T of ceil n by 2 plus n minus 1 minus what is T of n minus 1? T of floor n minus 1 by 2 minus T of ceil n minus 1 by 2 minus n minus 2. Now, floor n by 2 is same as ceil n minus 1 by 2. Because of this, these two terms they cancel, because floor n by 2 is same as ceil n minus 1 by 2, we have just now proved, and the value here is 1 less than the value over here. Therefore, this is equal to T of ceil n by 2, T of ceil n by 2 minus T of ceil n by 2 minus 1. This expression is T of ceil n by 2 minus 1 plus 1, because you have n minus 1 and from this n minus 2 is subtracted. So, you get plus 1. Let me write in a clean way. Plus 1. These two terms they cancel. So, let me do the cancellation like this. They are being cancelled. Now, look at the beautiful pattern. The difference of T, they follow a pattern. Suppose you define D of n to be T of n minus T of n minus 1. Then this is dn and this is d ceil n by 2 plus 1. So, d of n is d of ceil n by 2 plus 1. What a beautiful relation you have got for d of n, right. So, d of n is d of ceil n by 2 plus 1. We are going to show by direct expansion, right, because there is a one variable that is working and with a smaller value we iterate, okay, and then we are going to show that d of n is ceil log n. D of n is ceil log n. This is what we are going to show. Okay? So, we will go about showing d of n is in fact ceil log n. That is what we will show next. Okay? So, we will continue our discussion and the related mathematics. So, what we have seen is upper bound is obtained by using evaluating T of n exactly for infinitely many values and using monotonicity, guess and verify. We have done all of them and got upper bound. Now, we are in the process of looking into the details of the mathematics that gives exact solution. We are preparing ourselves to do that. So, we are halfway through that, and what we have done so far is T of n minus 1 follows a very nice pattern. We will continue our discussions and complete the detail in the next session. Thank you.